So if you had to take a determinant of the inverse of a matrix, what's one equation that can really take away the load or the heaviness of the burden of doing so? And it turns out that there is one. And it goes all the way back to this equation. So let's say you have the coefficient of matrix A. Let's make that more legible. Let's say you have the coefficient matrix A. What happens when you multiply it by its inverse? What happens when you multiply it by its inverse, you end up getting the identity matrix. Now, what if we were to take the determinant of each term like such, and it turns out that it equals to 1, and we know that the determinant in this case, let's say it can't be 0. It has to have an inverse in order for us to use this equation. And if we were looking for a determinant of the inverse of the matrix, can't we just divide both sides by the determinant of the coefficient matrix? And that ends up looking like this, where we have 1 over the determinant of the coefficient matrix. And there we go. That's the theorem that we're going to need. And it's going to help us a lot. So, we got that down. Let's start with a numerical instance. So, say you're supposed to find the determinant of the inverse of this given matrix. Where do we even begin? Well, let's start with finding the determinant of the matrix. So you go ahead and pause the video, do it yourself, work out each step, or you can plug into a calculator for my instant result. But in this video, I plan on expanding by rows, and more specifically, the first row. So we end up getting 1 times the 2 by 2 matrix of -1, 2, 1, 0. And then anything times 0 is 0. So we're only concerned with 3 times the 2 by 2 matrix, which is 0, -1, 2, 1. If we can work out the math, that ends up giving us the determinant of 4. Okay, now let's recall that the determinant of the inverse is equal to 1 over the determinant of the given coefficient matrix. As a result, the determinant of the inverse ends up being 1/4. Okay, that's perfect. We found the determinant of the inverse of a matrix. Now, can we apply that to a system of linear equations? Yes, we can, and let's get right to it. So let's say you're given these systems of linear equations, and you're asked to find which of the two has a unique solution. Okay, so let's think about this. What does it mean for a matrix to have a unique solution? It usually means, does this matrix have an inverse? Is it non-singular? And how can we prove that? Well, just like with all systems of linear equations, why not convert the systems to augmented matrices? Let's start with that. Okay, we converted the systems to augmented matrices. And let's look at part A. Do you guys notice something about columns 2 and 3? And if you do you remember anything about telltale signs that tell us whether or not a matrix has a determinant 0? And it turns out that when columns 2 and 3 are multiples of each other by, let's say here, -2. That fact confirms that the determinant of this matrix in part A ends up being 0. And as a result, part A does not have a unique set of solutions and is therefore singular. Now let's look at part B. So part B, columns 2 and 3 are not multiples of -2 or +2, and none of the rows or columns are equivalent to each other, nor does there happen to be a whole row or columns with zeros. So it does have that would mean that there is a unique solution, and that would indicate that the determinant of that matrix in part B is not 0, but we still have to solve it. And we can do that by row expansion, or we can just plug the calculator for an instant result. I'm going to go with row expansion in the first row. So 0 times anything is 0, and we are left with 2 times 3, 1, 3, 1, plus -1 times 3, -2, and 3, 2. Let me just zoom on out for you guys. And as a result, we get -12. And therefore, the matrix in part B has a unique set of solutions. And there you go. We were able to apply the properties of determinants to basically find the determinant of the inverse of a matrix and integrate that into systems of equations.